Thank you for that very kind introduction. Hello, everyone. Thank you to the organizers for inviting me. Very happy to be here. Um, so I'll just get started. I'm going to have my slides, so I won't actually see your faces. So I think there's, I don't know, if just speak out or raise reaction or something if you want to ask a question. Like don't worry about interrupting me. That should be fine. Okay, so the title of my talk today is Reinforcement Learning Can Benefit from AutoML. This is an AutoML workshop, so I wanted to try to connect some of the ideas that we're thinking about in reinforcement learning with some of the broader ideas that your community is thinking about. And the subtitle is The ALE Can Help, and I'll explain what the ALE is. And a lot of this talk is sort of centered around this ALE. So you've probably all heard of reinforcement learning by now. This wasn't the case a decade ago. Very few people had heard of reinforcement learning back then. And probably one of the main reasons most people around the world now have at least heard of reinforcement learning is because of these LLMs and the use of reinforcement learning for fine-tuning them. This started with ChatGPT in 2022, but reinforcement learning has been around for a lot longer than that. And it already had some pretty impressive success stories before ChatGPT. So from 2016 to 2021, we had AlphaGo, which was a major breakthrough where we could use reinforcement learning to actually beat world champions at this very complicated game. Myself and some colleagues, we used reinforcement learning to fly a stratospheric balloon. That's pictured here. And this was to deliver internet to remote areas of the world. This was a collaboration with Loon. We've used reinforcement learning for fusion projects and for chip placement. So these are all very real world applications, very complex, and reinforcement learning was one of the key ingredients in making these success stories. But it goes even back further. So in 2015, the DQM paper was introduced, and I'll talk about this in a little bit. This was, I'd say, the first major breakthrough of DeepMind, where they demonstrated that the coupling of deep neural networks and reinforcement learning algorithms allowed them to train agents that could play these Atari games at superhuman levels. And I'll get back to this in a little bit. But this is really where I think the field of reinforcement learning started to get more and more known and more used. But reinforcement learning has been around for far longer before that. The book I used to learn about reinforcement learning during my grad school was Reinforcement Learning, the book by Sutton and Bartow, which was the first version was published in 1998. And reinforcement learning, the concepts go back way before then. This is a picture of Andy Bartow and Rich Sutton, not 1979, but this is when they sort of started thinking about these ideas. And a lot of these ideas come from cognitive science, from neuroscience, control theory, optimization, and they sort of combine them into this, what we now know as reinforcement learning. Okay, so at a high level, if you don't know reinforcement learning, I'll give a very brief introduction to this. Reinforcement learning, we're mostly interested in training these things called the agent. So what is an agent? An agent is some entity. It could be an LLM, it could be a robot, it could be a game playing bot that interacts with an environment. And so the environment is where the agent lives. This could be a chessboard, it could be a Go board, it could be a physical room, it could be the stratosphere with the balloons. It's basically where the agent will be interacting to try to perform some task. And the way the agent interacts with the environment is by choosing actions. So this could be, move forward or make this move. In the case of LLMs, it would be, pick this token, use this as the next token, etc. And then the environment will give it the agent a reward or a cost. This is what we call the reinforcement, and this is why we call it reinforcement learning. This is what the agent uses to learn about whether whatever action it picked was good or bad. And it also gives it a new state. So what I mean by state is where the agent is. We define these environments as formally as Markov decision processes, although I won't go into the details of that. And these Markov decision processes have a set of states. And you can just think of this as a finite or an infinite set of locations, if you will, that the agent can move around. And how the agent moves around is determined by the environment dynamics. So the agent will take this new state, this reinforcement it receives, and incorporate it into its learning algorithm, and ideally improve the action selection. And this action selection, we typically call it the policy. So the policy maps a state to an action or a distribution over actions. So just to take a very simple example, let's say we have our agent here and it's trying to get to this star over here. So we can look at this, and this is a trivial problem, right? If we know the model, so if we can see the full grid, this problem is typically known as planning. So here we just have to come up with a plan how to get to the star as quickly as possible. And one route could be go right and then go the way down. Okay, easy, we've solved it. In reinforcement learning, we typically assume that the model is not known. So the agent starts here and doesn't actually know what else is around, and might not even know how big the space is, might not even know if there's a reward or how frequent the rewards come, or if there's reward or penalties, etc. And so the task of reinforcement learning is to try to figure out what's in this world and how to act optimally in this unknown world. So the agent might move around a little bit and sort of discover parts of the state space. So the state space is everywhere the agent can be, and maybe it's discovered these areas over here, and maybe it found a little star over here. So it thinks, okay, that's pretty good, but there might be an even bigger star down here. It just the agent hasn't seen it yet. And so this is one of the central challenges of reinforcement learning that's been around for decades and studied for decades, this notion of exploitation exploration. So at this point, the agent can decide to simply exploit its current knowledge. So it knows how to get to this small star here, and you could just say, okay, I'm happy with that, and I'll just stick with that because I know what's going to happen, it's safe, etc. Or it could decide to explore and go into this unknown territory. It might find this big star, but it also might find some other scary things. And so this balance of exploiting and exploring is a really central challenge of reinforcement learning, and there are a variety of different approaches to deal with it. So reinforcement learning, when I was doing my grad studies, we mostly dealt with these simple systems like this, which we call grid worlds, because most of the work we were doing was theoretical. The compute we had at the time was not at all up to the standards that we have today. Neural networks didn't quite work yet. So there was something we just kind of scoffed at and didn't even consider for reinforcement learning. So we were more interested in convergence proofs and having bounds on how many samples you need, or bounds on value estimation, things like that. But then in 2013, my good friend Mark and some colleagues introduced the arcade learning environment, or it's known as the ALE. And this is a suite of environments for reinforcement learning agents where each environment in the suite is a different Atari game. So this is the Atari 2600 console. This is something that was developed in the late 70s, and it was developed for humans to play, for people to play in their homes. And the games were developed not just by Atari, but by a whole bunch of different enthusiasts and some small companies and things like that. And they were all, they had ideas for what would make a cool game. And so they designed the games, all most of them controlled using this joystick. And this proved to be a really interesting challenge because the games are quite diverse, and they're kind of hard to play. This is why we like to play them, because they're challenging. So I'll come back to these games in a little bit, but the introduction of this benchmark really set a nice goalpost for reinforcement learning researcher. How can we get to human level, or ideally superhuman performance under this benchmark? So Mark and a few others, I think, were hired by DeepMind, which was a small startup at the time, and they worked hard on this benchmark. And in 2015, they published this paper in Nature, which was the DQN paper that I was referencing before, where they coupled reinforcement learning with neural nets. So this is 2015. AlexNet was in 2012. So by this point, people were already, at least in the ML community, were pretty convinced of the power of neural networks. And Vlad Min, he did his PhD with Jeff Hinton, so he knew neural networks really well, but he also knew reinforcement learning really, really well. So he was an ideal person to work on this combination, and of course, a bunch of other people at DeepMind. And they came up with agents that could play these games at superhuman levels and really demonstrated the power of this combination. And you can see, if you look at Google Trends, that since the publication of DQN, the interest in reinforcement learning has really been steadily increasing. And it's been sort of moving in parallel with the general interest in deep learning, which I'd say started with AlexNet. So reinforcement learning since then has been used quite successfully for many of the real world problems that I mentioned that are very complex. And it all started with this game or this suite of games that's the arcade learning environment. And since then, the whole community has been it's grown enormously. So when I used to go to conferences, this was when I was doing my PhD. This was before 2010. The conferences with reinforcement learning community was very small. I mean, I knew pretty much everybody in the community. Now there was a workshop at NeurIPS, a deep reinforcement learning workshop, a workshop that was 1,000 people. Like that's already a conference, and it was just a workshop. So this field has really grown a ton. And one of the ways, and this is something that started bugging me a few years ago. So I noticed in a lot of papers introducing new ideas or new algorithm, the standard way to do these things is you'd come up with a motivation. We want reinforcement learning to be more sample efficient, or we want it to handle bigger problems, etc. You have some baseline algorithm. Let's say we're going to build on DQN and then improve something by whatever, doing double DQN or having ensemble heads, whatever, some algorithm. Often you have some theory, and this used to be almost like a requirement, as Zach Lipton would put it, the mathiness that you had to have in papers to convince reviewers. But the theory in reinforcement learning, even now, really only holds up to linear function approximators, which are not neural networks. Neural networks are nonlinear function approximators. So you come up with this theory. It's usually for tabular systems where you basically store everything in a table. Linear function approximator is a bit more complicated, but we can still do some theory there. That's nice. Then you take that theory and you say, okay, I'm going to convert this into a loss. And this is going to be my fancy new idea. This is my new deep reinforcement learning algorithm. And so I'm going to test it on a common benchmark like the arcade learning environment. And then, I'm going to have a plot that ideally shows that my line is above the baseline's line. And that shows that my algorithm is better. And hopefully, I guess iClear, that was the deadline was an hour and a half ago. iClear accepts the paper. And that's great. Okay, so that's cool. That all seems nice. You had a very clear line of how you introduced this idea, but the devil is in the details. So this fancy new idea is something that you can't just take to a different problem. Let's say like these robot vacuum cleaners. I have one and it never works. I hate it. It gets stuck all the time. It stops, it runs out of battery. It doesn't actually pick up what I want it to pick up. So you could think, let's apply reinforcement learning here. Let's take this latest paper and implement it in this robot vacuum cleaner, and almost never works. And the reason it almost never works is because there's a lot of details that are really central to whether your algorithm works or not. And the theory tells you one thing, but what actually makes it work well or not when you're evaluating is what's in this blue rectangle here. And what's in this blue rectangle? Well, you have the base algorithm that you based yourself on. What's the network architecture and the network details that you use for your function approximators? What optimizer you use? What are the parameters for the optimizers? There's reinforcement learning specific components like replay buffers, and a whole bunch of other stuff. So these are what we know as hyperparameters. Often you end up just basing yourself on the hyperparameters of the base algorithm, and you might have to tune a little bit. But there are many algorithms where you can get either destroy their performance or get even much better performance just by tuning the hyperparameters. No need to change anything theoretical or algorithmic in it. So this is what really stops us from implementing a lot of these algorithms in real systems, or what makes it really difficult to do. But it's kind of weird because we still see progress. If you look at the literature, we do see progress. These are some algorithms that were based on DQN. And each one of these, if you read the papers, it seems to be improving on what it was building on. This is taken from a paper we published a few years ago. Actually, no, this is yes. This is from a paper we published a few years ago. Don't worry about the dashed lines. Just look at the colors. So this is really showing a kind of clear progression from DQN in blue all the way to IQN. So you see this very nice clear progression. We're making progress, right? These plots are aggregating. These are evaluated on the arcade learning environment, but they're aggregated over multiple games. So this is an aggregate plot. But when we look at the individual games for these same algorithms, it's quite a different story. So you can see if you just look at the ordering of the different algorithms, the ordering is very different from game to game. So if you look at here, C51 is killing all the other games here, but it's one of the worst algorithms in this game. And pretty much any game, any ordering you want, you can probably find a game where that ordering is respected. So this is kind of weird because if we come back to this figure, when we look at it, things in aggregate, it looks very clean. You see progress. That's very nice. But when you look a bit closer, you can see that the ranking and the distinction between algorithms is not as clear cut. So to sort of exemplify this issue, I'm going to tell you the story of a couple of papers that, or a few papers that were published a few years ago. So Rainbow, I mentioned as this was one of the algorithms that I was discussing. This is another paper by DeepMind. And what they did here is they took a whole bunch of recent algorithmic improvements. So they started with DQN, and then they added a bunch of ideas from different papers like dueling networks, prioritized replay buffers, double DQN, distributional reinforcement learning, noisy networks, etc. And they combined all of these. And this is why they call it Rainbow, because it was just like a combination of a bunch of different algorithmic colors. And they showed that their algorithm really improved just by combining these things. It gave really, really big improvements. And Rainbow is still like one of the strong algorithms today. So that's nice. But then later, some other folks came around, and they were working. This was very early work in what we now know as world models, and very early work also with transformers. So they were using like some of the early versions of transformers to have a world model for reinforcement learning. What I mean by a world model is that you're learning to kind of a simulator, an internal simulator of the environment dynamics. And so then you can, with that, you can do planning without having to interact with the environment. And what they showed is that this plot, this red line, this is showing how many environment interactions their algorithm needed in order to achieve human level performance. And the blue bars show how much Rainbow needs. So basically, the point of this plot is showing, this Rainbow algorithm is really, it seems to be really great, but when you're trying to reduce the number of environment interactions, and this is often what we call sample efficiency, Rainbow is not that great, and our algorithm is a lot better. Okay, that's kind of nice. And they introduced this new benchmark called the 100K benchmark. So if you see here, this 200, this is 200 million frames. So that means those are Atari game frames. So this is still pretty much, I think, that the most standard way of evaluating Atari games. You let them run, the agent can interact with the environment for 200 million frames. It's still quite a lot. And so what this paper was arguing is like, we should be more efficient than that. So we're only going to give the agent 100K environment steps. And this is how, with 100K interactions, we were able to achieve very good performance. Okay, that's great. And Rainbow, they're arguing, is not as sample efficient. But then the Rainbow authors came back and said, no, wait a second. We tuned our Rainbow for 200 million interactions. If we maintain exactly the same algorithm, but we just retune the hyperparameters, now we can outperform your model-based algorithm. And this is the red line here. And this is what they call data-efficient Rainbow. So data-efficient Rainbow is exactly the same algorithm. It's just different hyperparameters. That's it. And this is what I was mentioning about the importance of this blue rectangle, these hyperparameters, on making or breaking algorithms. So there was no algorithmic contribution here. It was really just a question of hyperparameter tuning. Okay, so based on all this and other ideas that we were thinking about, with a few of my students, we published this paper at RLC, which is a Reinforcement Learning Conference, last year, where we were exploring this space of hyperparameters. And in particular, we were interested in this ranking of different hyperparameter choices. So if you have one, let's say, learning rate for your optimizer, you can choose from a few different options. How do you figure out which is the value that you should pick? So typically you have, a subset of the games, and you tune on that, and then you find the best one, and that's what you use for your evaluation games, and hopefully it works well. So that's the type of question we were looking at, and we investigated all of these hyperparameters, which are kind of standard hyperparameters in reinforcement learning. And we did that for two common algorithms in reinforcement learning, Dr. Q and DER, which is the one I just mentioned right now, which is the rainbow but tuned for the 100K setting. And Dr. Q was also introduced mostly for that 100K benchmark, so low samples allowed from the environment. And these are two pretty standard environments for that low environment interaction setting. And three questions we were asking ourselves is, if we are selecting these hyperparameter selections in one setting, how well do they transfer to a different setting? So in particular, if we, let's say, tune hyperparameters according to using Dr. Q, how well would those hyperparameter choices transfer to DER? If, let's say, we tune our hyperparameters in the 100K setting, which is much cheaper, how well would those choices transfer to the 200 million setting? Or, I mean, we only did 40 million just for computational, so that it wasn't so expensive. And another thing, which I already hinted at before, if we tune hyperparameters in one set of environments, how well does it transfer to another set of environments? And so we came up with this THC score, or tuning hyperparameter consistency score. We're basically, I won't go into the details, but what it's trying to quantify is how consistent are the rankings across these regimes. And so so what we want to have is actually lower values. So we can see that, sorry, we want to have higher values. So higher means more consistency. So the lower the values, the less transferable those things are. So you can see things, like the replay history are really hard to transfer. They don't transfer very well. Batch size in the 100K regime doesn't transfer well across agents, etc. So I'll spare you a bit of the details of this analysis. You can look at it in the paper. What I wanted to show was a few examples that highlight what that table was trying to summarize. So for the first question, how well do hyperparameters transfer across agents? For the two agents we considered, we found that they generally transfer pretty well. It's not perfect, so you can see like the discount factor. There are some differences here, but in general, it's relatively consistent. So we found that it was relatively easy to transfer, and this is not terribly surprising. Perhaps these are both algorithms that are based on DQN. So if you're starting from the same base algorithm, then maybe there's a bit more consistency there. Across data regimes, things were quite different, so they don't really transfer well at all. And in particular, if we look at this, we're looking at the epsilon value in ATOM. So ATOM has this ATOM optimizer has this epsilon parameter, which when you read its description, it feels like it shouldn't affect anything. The only reason that epsilon there is it's used in the denominator in this ratio that's computed by ATOM, just to avoid divide by zero errors. So really, it's just a numerical trick to avoid blowing up those ratios. But it actually turns out that our algorithms are very sensitive to that parameter. And if you were to tune in 100K, you can see that this green value is doing really, really terribly. And so if you were to tune in 100K, you would say, no, this is the worst value, and I'm not even going to consider it. But if you let it train for longer, for 40 million frames, you can see that it becomes actually the strongest hyperparameter choice for both algorithms. And it kind of flips. So whatever was at the top ends up being the worst choice when you train for longer. So this was a pretty surprising finding, because a lot of papers kind of present things either in one regime or the other and sort of assume that the findings will transfer. This is not really the case, as we're finding here. Do they transfer across environments? I already hinted at this before. Not really. So you can see here, this is the batch size that we use for training. And you can see in these two environments, the ordering is completely reversed, right? So if you were to tune your batch size based on Gopher, you'd get the worst performance on Kangaroo and vice versa. And you can see this across many games, and not just for batch size. There are many hyperparameters where you see this ranking sort of all over the place. And that was for Dr. Q. For DER, you also see this is for the discount factor. You see, pretty much any ordering you want to find, there's a game that has that ordering, which is quite frustrating, because then how do you, which was the right discount factor to use? So here's the paper if you want to check it out. There's a lot more details and more plots there. We also have a website, which is linked here, where you can actually play around with these things and not have to navigate through a PDF, which is kind of annoying. And we ran a lot of experiments for that, so you can play around with that. So one of the takeaways for me from this was kind of depressing in a sense. We feel like we've made all this progress in reinforcement learning, but yet when we look at the details of the per game details, we see that we can't really get these algorithms to work reliably, even in this game environment, these Atari games. And you know, a lot of people in the reinforcement learning community feel that Atari is over, and we solved it. We don't need to do anything there. I completely disagree with that. And I hope the plots that I was showing before indicate that we're not quite done there yet. There's lots we don't understand, and there's lots, you know, our algorithms are not uniformly outperforming every other algorithm across all the games. So if we can't even solve these problems reliably in Atari games, what hope do we have for, you know, these robot vacuum cleaners and other more complex real world systems? So one of the things I've been arguing over the past few years is that this ALE can still, you know, despite what people say that it's boring or it's useless and it's solved, it can still be a really great benchmark for making meaningful progress in reinforcement learning, and in particular for auto reinforcement learning, or more generally AutoML. And some of the reasons for this I'll explain here, and then we can have a discussion later. So as I mentioned, the ALE was introduced with all these games that were developed by different people, different communities, different companies. They were developed a long time ago for TV systems that were very different than what we have today. These were, you know, they were actually doing scans across the screen, and so you had to. Computers were a lot slower. They had an actual laser that would, you know, or a beam that would print the images on the screen, and then when it got to the bottom right, it had to go back to the top left, and that time, just for the beam to go from the bottom right to the top left, that's when they could do their computation. So they really had to. The games had to be designed in a way that they could, you know, update game states and things like that very quickly when it's just doing this, moving the beam back, physically moving a beam. So these types of constraints we don't think about these days anymore, because, you know, we're in the silicon age and everything is kind of cheap and infinite and whatever. But they're very diverse, these games, so they have very different challenges. They were developed by different people, as I said, and so this diversity is quite good. And what I mean by non-biased is that they were not developed for reinforcement learning research. They were developed for people to play and have fun. And so this is very different from a lot of the environments that have appeared since the DQM paper. You know, people are interested in exploration, or they're interested in I don't know, multi-agent gameplay, and so they'll design their own environments, which is fine, but there's a bias there. There's an experimenter bias, right? You're trying to find a way to showcase your new algorithm, and so you design an environment that showcases that capability. I mean, that's sort of like Goodhart's law. Like you're optimizing for the metric that you said you'd optimize for. So that's the nice thing about this. There's no bias, no experimenter bias in that sense. And within each game, we can also have what are called modes, or difficulty modes. So you know, at the top row, this is the standard way of playing the games, but you can make them more difficult or easier. So for instance, in Space Invaders, you can make the aliens invisible, and that, you know, just makes the game a lot harder. I don't remember Asteroids. I think things move around faster or something. In Breakout, you can make the ball move faster. In Freeway, which is a road crossing game, you can make, you know, trucks appear or move faster or slower, etc. And these game modes, what's interesting about it is, you know, if you look at it, well, except for Space Invaders, but if you look at Breakout, it's basically the same game, just a little faster. And so you would expect an agent to be able to, that's trained on one mode, to be able to transfer pretty easily to another mode. And it turns out that that's not the case. They're really terrible at transferring. And this is one of the challenges of these types of agents, that they're very overfit to their current environment, and having them be generalizable is quite difficult. So these modes, they present an opportunity though for testing things like generalization, for also for testing, the generalizability or the transferability of hyperparameters across these modes. So you're still within roughly the same environment, just some of the dynamics are changed a bit. And do your hyperparameters transfer there? That's a kind of an open question. Most of the environments that I don't know if most, but a lot of the environments that people deal with are deterministic in the sense that if you perform an action, you know exactly what the next state will be. If you think of LLMs, when a token is picked, the token is what's selected. It's not like you pick the letter or the word, let's say cow, and then the LLM for some reason decides to override your choice and put dog or something. If you select cow, you'll get cow as the next word. But the more general formulation is stochastic. So if you think of a robot navigating a room, you might say go forward, but maybe the floor was slippery, and so it actually ends up staying in the same spot. And so this stochasticity makes problems more difficult. The ALE allows both deterministic and stochastic transitions, which again is just another dimension where you can explore some of these ideas of AutoRL and algorithmic stability. Another important concept is the action space. So I mentioned that you normally play, or when Atari games were introduced, most of them played with this joystick, which is this thing that as humans we take our hand and we move it, we move it around. It's a continuous movement that we're doing. And under the joystick itself, there are discrete pins, so it does only trigger a set of 18 possible joystick configurations. So it is a discrete joystick, and that's what Atari has been built on. But if we think of the ultimate goal of having these autonomous agents that don't have to rely on these emulators or simulators that we built, but can actually go and interact and pick up coffee cups and whatever. For real in the real world, you want them to be able to interact in this non-discrete manner, so in a continuous type of manner. And so this is something we introduced last year at NeurIPS, where we added support for these continuous actions. So you can move the joystick in all sorts of positions, have it in all sorts of positions, and how the events are triggered depends on, this is something you said with this tau, but it still ends up triggering the discrete events just like the original controller, but the action space that the agent has to choose from is continuous, which makes it a lot more challenging. And again, this is just another dimension that we can explore. These are some results on using this continuous space, and you can see it makes things a lot more difficult, but not always. Again, this comes back to this point about the wide variety of results we get across games. So for the most part, we see that that the discrete version of the environment, which is the brown line or the beige line here, is much easier than the continuous version, which is the blue line. We're just able to make a lot more progress. But when you look at it at a per game level, you can see that sometimes the blue line is above in some games. So there's something kind of interesting there, and worth exploring a bit more. And finally, another reason why this ALE is quite interesting, I find, for doing this type of research of AutoML. And when I say AutoML, or AutoRL, one of the things I'm really thinking about is how to select these hyperparameters, which is kind of a theme of what I've been discussing today. Typically we pick one hyperparameter, we say we're going to use this learning rate, and that will stay throughout the training of the agent. Sometimes there are optimizers that can do learning rate decay or have some type of schedule, etc. For some hyperparameters, you have that, but you still have to pick that schedule, and you still pick that decay kind of globally, and that is used for all games and all settings. For most of the other reinforcement learning hyperparameters, like the discount factor, the batch size, etc., those remain fixed throughout training. And if they change a little bit, again, it's the same schedule globally. What I think we should be doing is having these hyperparameters being set automatically throughout training, and in a way that's using characteristics from the environment to decide what to do. And so one of the I think I have a slide later. But one of the things I'm also quite interested in is coming up with more formal and quantifiable characterizations of the environments, so that we have some high level descriptions. So you may have heard of Montezuma's Revenge. This is known as a hard exploration game. I mentioned the exploration exploitation problem, but this is a pretty high level thing. And often hard exploration just means that it's sparse rewards, or you don't get rewards very frequently. But that's not enough. I think we need to have more a better understanding for what sets these games apart. So, for instance, why is bowling so much easier with continuous actions than breakout? Let's say, I have some theories, and I can look at the videos and come up with hypotheses. But really, what I'd like our agents to be able to do is to start interacting with the environment, and kind of decide, okay, this is an environment that has these characteristics, so I'm going to drop the learning rate, I'm going to increase the discount factor, etc. And throughout training, change those things, right? Because you'll be in different areas of the state space. This is one of the things that also makes reinforcement learning quite challenging relative to something like supervised learning. If you think of like image classification problems, you start with a data set. The data set has labels, and that remains fixed throughout your training. So it's a stationary problem. In reinforcement learning, you don't have a data set. You have data that you collect from the environment. And how do you collect data from the environment? With your policy. But your policy is what you're optimizing. So the policy is changing throughout your training, which means that the data that you're using to train on is changing. And also, in reinforcement learning, the loss, we don't have a clear notion of target, or a fixed notion of target, in the same way as for instance, image classification. The targets we build based on our prior estimates, right? And this is what we call bootstrapping. So if our estimates are changing and we build our targets based on our estimates, then our targets are also changing. So reinforcement learning has non-stationarity both on the data space as well as on the target space. So it's very, very challenging. And so this is why I think it's extremely important for us to be able to come up with methods that are able to automatically adjust hyperparameters to account for that non-stationarity. So, the ALE, as I mentioned, it was sort of seminal in the sense that it allowed DeepMind to demonstrate the power of combining these things. It's still used a lot in research, and these numbers, every time I give this talk, I have to take the screenshot again because the number keeps growing. And I feel it has all the pieces for making meaningful progress on this type of AutoML or AutoRL type of research. And so just to end off, again, mostly focusing on the ALE, but with its connections to this field of AutoML and AutoRL. Something that I hinted at a few times during the talk is this notion of presenting these aggregate results. So these aggregate results, it's using this interquantile mean, which is something that actually we introduced in a paper a few years ago, which is a very statistically robust metric, and that's nice. And it makes it nice for papers because it's just one plot as opposed to having 60 plots for all the 60 games. And it does give statistically meaningful comparisons of algorithms. So I think it is good, and we shouldn't stop using them necessarily. But we can't just stop there. We have to look at the individual games, and we have to look at these differences, because there are many differences, and they're important. And if we really want reinforcement learning to be more universally used and easier to use, all the examples I gave of success stories for reinforcement learning, they all required a team of reinforcement learning experts to make it work. If you contrast this with like computer vision models, pretty much anybody can now download a computer vision model from Hugging Face and use it with their webcam and come up with some pet project. To do that with reinforcement learning on a new project is really, really hard. And you typically need years of reinforcement learning expertise to do that. So we need to get a better sense for how these environment differences, these per game differences matter. The other thing is, this is in the same paper where we introduced this metric, we were looking at the distribution of scores. So there is variability in the performance we get from algorithms. And when we deploy an agent in the real world, it's not like we can deploy 5 seeds and then pick the best seed. We have 1 seed, right? That's the one algorithm we deploy. So we also want to get a sense for the variability of the results we get. And so looking at the consistency of our results, or the distribution of our results for our algorithms, is important to get a sense of the uncertainty of its performance. The 100K benchmark that I mentioned, one of the things that it also, a design choice that they made, is that they didn't use the 57 games that DQN was using. They used just 26. The reasoning for their choice is that these were the only games where they were able to make any meaningful progress in 100K interactions, which is fine. But now I feel like the community ends up overfitting on that, and so they only do the 26 games. But there's a full suite of games that we can still explore, and that we can still get signal from for improving our agents. And in fact, nowadays I think there's 60 that are kind of standard 60 games, but there's a lot more that can be used. And Michael Bowling gave a talk at RLC this year on the history of the ALE and how they selected those games. So it turns out there's some games that are adult themed, and so they didn't want to include those. There's because anybody could make these Atari games, right? So people in their basement could make their games, and so there's hundreds of games out there that we could also consider exploring. We also the how long you run your agents for matters, as I already mentioned. So one thing that we should really start doing is running them for longer, because we don't really know a priori how long we're going to need to train our agents for, especially in new problems. And I mentioned the characterization of games. There's been some work already in trying to do this beyond just saying, this is a hard exploration game, but I think there's a lot more that we can do there. And in particular, not just games globally, but where you are in the game or the environment, I think is important to get a better characterization for. So again, to come back to what I was hinting at before, I feel that the AutoML and AutoRL community has an opportunity to make many of these RL algorithms dynamically adjust themselves. So dynamically adjust hyperparameters and settings based on quantifiable environment characteristics. And I feel that the ALE is really well suited to be able to do this for all of the reasons I mentioned above. There are some considerations and some concerns with the computational cost of it, but with modern software tools like vectorized GPU environments and things like envpool, we've really been able to bring down the compute requirements for this quite a lot. If you're interested in the history of Atari, this book is fantastic. I can't recommend it enough. Even if you don't do RL, if you just like video games, it's the thing I was mentioning with the beam. This is where the title of this book comes from. It's Racing the Beam, because the software developers were actually racing against the beam to be able to have the computer logic. It's really fascinating read if you're interested in that. This is my website. It's quite out of date. I think it's been over a year since I've updated it, but I'll get to it hopefully before the end of this year. Yeah, and once again, thanks for inviting me. Happy to take some questions. I don't know how much time we have. Yeah, I hope to see some of you working in this space at some point.